Somewhere in the galaxy, right now, a dying star is quietly building toward an explosion so bright it will briefly outshine every other star around it combined. It hasn't happened yet, but when it does, the light will travel for thousands, maybe millions of years before it ever reaches a human eye. Here's the strange part. The explosion may have already happened. It might have happened before the pyramids were built, and we simply haven't seen it yet. Tonight, we're going deep into the most violent, most extreme, most physically unreasonable events the universe has ever produced, and we're going to let each one carry you a little further towards sleep. Hello, and welcome to Somniora Mind. I'm glad you're here. Before we drift into the cosmos tonight, if you find these long, quiet science journeys helpful for winding down, consider subscribing or leaving a comment or tapping the like button on your way towards sleep. It costs nothing, and it helps this small, quiet corner of the internet keep finding the people who need it. Now, let your body sink into wherever you're resting. Let your jaw unclench. Let your eyes close, if they haven't already, and let's begin. Here's what we'll uncover tonight. We'll find out how a metal you might be wearing on your finger right now may have been forged in a collision so violent it briefly outshone its entire galaxy. We'll discover why some of the most catastrophic explosions in the universe are also, secretly, acts of creation, seeding the raw material for planets, oceans, and eventually, people. And near the end of the night, we'll sit with something almost impossible to picture. A black hole that got physically kicked out of its own galaxy, still traveling, still alone, carrying nothing with it but its own darkness. Here's a number to open with. A single supernova, for a few brief weeks, can release more energy than our sun will produce across its entire 10 billion year lifetime. Not more brightness, more total energy compressed into a matter of days. The universe, it turns out, is capable of violence on a scale that makes almost every human unit of measurement feel a little absurd. And yet, as we'll discover together tonight, that same violence is rarely just destruction for its own sake. Again and again, across every scale we'll explore, from a single dying star to two entire galaxies colliding, catastrophe and creation turn out to be more closely related than they first appear. Let's start with the supernova itself, because it's the doorway into almost everything else we'll explore tonight. A star spends most of its life in a kind of extraordinarily patient standoff. Gravity is constantly trying to crush it inward, and the pressure from nuclear fusion in its core is constantly pushing back outward, holding that collapse at bay. For millions or billions of years, depending on the star's mass, this balance holds. But it cannot hold forever. Eventually, a massive star runs out of lighter elements to fuse in its core and begins building up iron. Iron is the turning point, because fusing iron doesn't release energy, it consumes it. The instant the core becomes dominated by iron, the outward pressure that has held the star together for its entire life simply stops being generated. Gravity, which has been waiting the whole time, finally wins. What happens next unfolds impossibly fast. The core, which might have taken millions of years to build up, collapses in well under a second. Electrons are driven into protons, forming a flood of neutrons and releasing an almost unimaginable burst of neutrinos, ghostly particles that barely interact with anything at all. As the core reaches nuclear density, matter suddenly becomes almost perfectly incompressible, and the collapse doesn't just stop, it rebounds, like a spring compressed far past its limit and then suddenly released. A shock wave rips outward through the rest of the star. Whether that shock wave successfully blows the outer layers away, producing the visible fireworks of a supernova, or whether it stalls and gets swallowed back into a forming black hole, is one of the most delicate and computationally difficult problems in modern astrophysics. When the shock does succeed, the result is spectacular. A single dying star can briefly become the brightest object in its entire galaxy, a galaxy that might contain hundreds of billions of other stars. For a short window of weeks or months, one star, one single point of light, can outshine that entire glowing population combined before fading permanently into whatever it leaves behind. Supernovae don't just destroy. They also announce themselves in ways that can be studied for thousands of years afterward. And in one remarkable case, they were noticed and written down long before anyone understood what they were looking at. In the year 1054, court astronomers in China recorded something extraordinary in their sky charts. A new star, brighter than anything else nearby, bright enough to be seen during full daylight for over 3 weeks, and visible at night for nearly 2 years afterward. They didn't know they were watching a star die. They simply wrote down what they saw, faithfully, the way careful observers do. Nearly 1,000 years later, astronomers pointed a telescope at that same patch of sky and found something strange, an expanding, glowing cloud of gas, now known as the Crab Nebula, with a rapidly spinning collapsed star buried at its center. When they calculated how quickly that nebula was expanding and worked backward, the timing matched almost perfectly. The medieval sky watchers, with nothing but careful eyes and careful record-keeping, had witnessed a supernova, and their notes, made for entirely different reasons, in an entirely different century, became genuine scientific data for astronomers 1,000 years later. It's a strange kind of collaboration across time, between people who had no concept of atoms or gravity and researchers today who are still studying the very same explosion. Chinese astronomers weren't the only careful sky watchers to record one of these rare, naked-eye explosions. In October of 1604, observers across Europe, including the astronomer Johannes Kepler himself, watched a brilliant new star appear in the constellation Ophiuchus, bright enough to outshine every other star and planet in the night sky, remaining visible even in daylight for several weeks before slowly fading from view over the following year. Kepler tracked it carefully night after night, and his detailed observations remain some of the most complete pre-telescopic records of a supernova ever made. What makes this particular event so remarkable, looking back, is simple longevity. It remains, even now, the most recent supernova to have been observed exploding within our own Milky Way galaxy, visible to the naked human eye, over 400 years ago now, and counting. Modern telescopes have since studied its remnant in exquisite detail, but no one alive today has ever personally witnessed a naked-eye supernova erupting inside our own galaxy. Statistically, our galaxy should produce a handful of these events every century, based on how many are observed happening in similar galaxies elsewhere in the universe. Which means, quite simply, that somewhere in the Milky Way, hidden behind dust, or simply not yet noticed, there are very likely supernovae that have already happened in the centuries since Kepler's, whose light just hasn't had the chance, or the clear line of sight, to reach us yet. There's an even stranger echo from a more recent supernova, one that arrived not through light, but through particles that pass through solid matter as though it barely exists at all. In February of 1987, deep underground detectors, built to watch for entirely different kinds of physics, registered a small, unexpected burst of neutrinos, arriving from the direction of a nearby dwarf galaxy called the Large Magellanic Cloud. Only about 24 of these particles were caught, across all the detectors on Earth combined. Hours later, astronomers spotted a new supernova blazing in that same direction, an event now known as Supernova 1987A. Those 24 neutrinos had been traveling for roughly 160,000 years, crossing the space between galaxies, arriving at Earth mere hours before the visible explosion itself. This tiny handful of nearly undetectable particles confirmed something theorists had predicted but never observed directly: that the overwhelming majority of the energy released during a stellar collapse doesn't come out as light at all. It comes out as neutrinos, an entire flood of near-massless particles, streaming outward through the collapsing star and into the universe within seconds, long before the visible shock wave has even finished fighting its way to the star's surface. In principle, if a star close enough to Earth ever collapses again, our neutrino detectors could give astronomers advance warning, sometimes hours, before the star visibly brightens. In a very real sense, the universe would whisper that something has died before it ever shows us the light. A supernova's brightness doesn't simply vanish the moment the initial shock passes through. Many of these explosions keep glowing for weeks or months afterward, and the reason has nothing to do with the original blast at all. Inside the debris, the explosion forges enormous quantities of unstable, radioactive elements, nickel, 56 chief among them. That nickel decays into cobalt, and the cobalt decays again into stable iron, and every single one of those decay steps releases energy, which the surrounding gas absorbs and re-emits as visible light. This slow radioactive afterglow is often what keeps a supernova shining long after the actual explosion has technically already finished. By carefully measuring how the brightness fades over time, astronomers can work out how much radioactive material was actually created, giving them a window into the exact physics of an explosion that happened in the time it takes to draw a single breath. Even after the visible glow finally fades, a supernova story is far from over. The expanding wreckage, now called a supernova remnant, keeps racing outward for tens of thousands of years, slamming into surrounding interstellar gas and heating it to millions of degrees, hot enough to glow brightly, not in visible light, but in X-rays. Space telescopes tuned to those X-ray wavelengths can map exactly which elements are present in the debris, revealing oxygen in one region, silicon in another, iron somewhere else entirely, essentially reconstructing how the layers of the original star were arranged before it exploded, like piecing an entire onion back together from its scattered peelings, scattered now across dozens of light years of space. And remarkably, a star's death doesn't only destroy. It can, under the right circumstances, help build the very next generation of stars. When a supernova's shock wave slams into a nearby cloud of cold interstellar gas, it can compress that gas violently enough to trigger its own gravitational collapse, seeding the birth of brand new stars from the wreckage of an old one. The timing has to be just right. A shock that's too strong tears the cloud apart entirely, while one that's too weak barely disturbs it. But when the conditions line up, the death of one star becomes the opening act for an entirely new generation, born partly from material the old star itself once expelled. Destruction and creation, out here, are rarely opposites. More often, there's simply two stages of the very same ongoing process. One particular supernova remnant, Cassiopeia A, has become something like astronomy's favorite specimen for studying exactly this kind of stellar autopsy. Its parent star exploded roughly 340 years ago, close enough in cosmic terms, and recently enough in human terms, that its expanding debris field is still relatively compact, bright, and richly detailed. when viewed through modern telescopes. X-ray images of Cassiopeia A reveal a shell of material glowing in distinctly different colors depending on which chemical element is present: oxygen concentrated in some regions, silicon in others, iron scattered elsewhere still. Essentially a three-dimensional chemical map of a star's interior, blown outward and frozen mid-explosion for astronomers to study in exquisite detail. Centuries after the actual event, buried at its center sits a compact object, likely a neutron star, that appears unusually faint and quiet compared to more active pulsars like the one inside the Crab Nebula, offering astronomers a valuable point of comparison. One violently disrupted star, viewed at two very different stages of its long, ongoing afterlife. Not every stellar explosion begins with a massive star collapsing under its own weight. Some of the most scientifically important supernovae come from an entirely different kind of star, one that seemed, for all appearances, to have already finished dying long before its final, explosive act. A white dwarf is what's left behind when a star like our own Sun finally exhausts its nuclear fuel. It's not massive enough to undergo the kind of catastrophic core collapse we just described. Instead, it simply cools and settles into a dense, quiet, roughly Earth-sized ember, packed with the mass of a sun. Left alone, it could sit there for the remainder of the universe's existence, slowly fading toward darkness. But if that white dwarf happens to share a close orbit with a companion star, its story isn't necessarily over. Gravity can slowly pull a stream of gas away from that companion, funneling it onto the white dwarf's surface, layer by layer, over thousands or millions of years. As the white dwarf gains mass, conditions deep inside grow more and more extreme, until eventually, carbon buried in its core can ignite, all at once, in a runaway thermonuclear reaction that tears through the entire star in a matter of seconds. Unlike a core collapse supernova, this kind of explosion leaves nothing dense behind: no neutron star, no black hole. The white dwarf is simply, completely unbound, its material blasted entirely into space. Astronomers call this a Type I supernova, and its exact trigger, whether it's always a slow gas transfer from a companion or sometimes two white dwarfs colliding directly, is still an active area of research. What makes Type I supernovae extraordinary isn't just how they explode, but how astonishingly consistent that explosion turns out to be. Because they tend to detonate at very similar masses, these explosions reach very similar peak brightness almost every single time, which means astronomers can use them as what's sometimes called a standard candle. If you know how bright an explosion actually was, and you measure how faint it appears from Earth, you can calculate, with real precision, how far away it is, even across billions of light years. The exact trigger behind these explosions is still genuinely debated. In the more traditional picture, a white dwarf slowly siphons gas from a companion star until conditions in its core become extreme enough to ignite. But a growing body of evidence points toward a second, entirely different pathway: two white dwarfs, orbiting each other closely, gradually spiraling together over billions of years through the same gentle loss of orbital energy that drives neutron stars and black holes toward their own eventual mergers, until they finally collide or merge outright. If their combined mass and composition are right, that collision alone can ignite catastrophic carbon burning, producing a thermonuclear explosion essentially indistinguishable from a distance from the more traditional version. In some of these double white dwarf mergers, one star may be entirely disrupted first, forming a hot, unstable structure draped around its surviving companion just before ignition. In others, The violent compression of the collision itself may be enough to trigger burning almost immediately. Astronomers try to distinguish between these different pathways by carefully examining old supernova remnants for any surviving companion star. Since a double white dwarf merger should leave nothing nearby at all, no ordinary donor star left behind. Only empty space where two entire stars used to be. In the late 1990s, two separate teams of astronomers set out to use these explosions for something ambitious, measuring how quickly the expansion of the universe was slowing down under its own gravity. That was the expectation, that gravity, acting across the entire cosmos, should be gradually putting the brakes on cosmic expansion. Instead, both teams found something nobody had predicted. The distant supernovae appeared fainter, and therefore farther away, than they should have been if the universe's expansion were simply decelerating. The only explanation that fit the data was almost unthinkable. The expansion of the universe isn't slowing down at all. It's speeding up. Some unknown influence, since given the placeholder named dark energy, is pushing space itself apart at an ever-increasing rate. Nobody fully understands what dark energy actually is, even now. But the discovery, made by watching dying stars in distant galaxies, completely rewrote our understanding of the universe's future, and it earned its discoverers a Nobel Prize. A dead star's final flash became a ruler measuring the shape and fate of everything. There's a deeper story woven into ordinary supernovae too, one about where much of the periodic table actually came from. Stars can build elements up through iron using ordinary nuclear fusion. But fusing anything heavier than iron doesn't release energy. It consumes it, which means stellar fusion alone simply cannot manufacture most of the heavier elements you're familiar with. To build those, nature needs something far more violent. An environment packed with free neutrons and enormous amounts of energy, conditions that exist fleetingly inside certain explosive stellar events. Atomic nuclei caught in that chaos can capture neutrons far faster than they can decay away, climbing rapidly up the periodic table into territory ordinary stellar burning could never reach on its own. Every atom of iron heavier than what a star's core naturally produces. Every trace of certain rare, heavy metals scattered through the crust of our own planet may ultimately trace back to explosive violence that happened long before our solar system ever began to form. The ordinary matter around you carries a quiet, chemical record of ancient catastrophe. Not every dramatic stellar outburst is actually what it first appears to be, and a handful of stars have genuinely fooled astronomers into thinking they had exploded, when in fact, they hadn't. Certain extremely massive, unstable stars, called luminous blue variables, occasionally undergo sudden, violent eruptions, briefly brightening by a factor of 100 or more, expelling enormous amounts of material into space, closely mimicking the appearance of a genuine supernova. Unlike a real supernova, though, the star itself survives the eruption. Astronomers refer to these dramatic false alarms as supernova imposters, and one of the most famous examples, a massive, unstable star called Eta Carinae, underwent exactly this kind of eruption in the mid-1800s, briefly becoming one of the brightest stars in the entire night sky, before fading back down over subsequent decades, all while the star itself remained fully intact, hidden inside the expanding, glowing cloud of material it had violently expelled. Eta Carinae is still there today, still unstable, and many astronomers consider it a strong candidate to undergo a genuine supernova at some unknown point in the future, possibly within the next few 100,000 years, an almost instantaneous span of time by cosmic standards. These imposter events remind us that even among the most extreme stars in the galaxy, The line between nearly dying and actually dying isn't always obvious from a distance, and sometimes a star can throw an explosion dramatic enough to fool careful, patient observers for years, all while quietly continuing to survive. Some stellar deaths break every one of these rules entirely, and they're rare enough that astronomers are still hunting for solid, confirmed examples. Picture a star so enormous, hundreds of times the mass of our Sun, that its very core reaches temperatures extreme enough for photons themselves to start spontaneously transforming into pairs of matter and antimatter. That transformation quietly removes some of the radiation pressure that had been holding the star's interior up against gravity at exactly the worst possible moment. The core contracts further, temperatures spike even higher, and oxygen fusion suddenly runs away completely out of control. Instead of the gentler collapse and rebound sequence of an ordinary supernova, the resulting thermonuclear reaction can be powerful enough to blow the entire star apart, with nothing left behind at all. No neutron star, no black hole, just scattered debris, expanding outward into the galaxy. Astronomers call this a pair-instability supernova, and the stars capable of triggering one are thought to have been far more common in the very early universe, when stars could form from primordial gas containing almost none of the heavier elements that make this process harder to trigger today. Finding a confirmed modern example would let astronomers witness something genuinely rare. A star erased so completely that it leaves absolutely no compact remnant of its own destruction. Other explosions seem to defy expectation in the opposite direction, not by disappearing without a trace, but by refusing to fade on any normal schedule at all. In certain extraordinarily luminous events, astronomers suspect the newly formed neutron star at the center is a magnetar, spinning at an extraordinary rate right after birth, holding an immense reservoir of rotational energy. As its intense magnetic field gradually slows that spin down, some of that stored energy gets funneled directly into the surrounding supernova debris, keeping the whole explosion far brighter for far longer than ordinary radioactive decay alone could ever explain. These are called superluminous supernovae, and the leading theory is essentially this. The very object born inside the explosion may begin powering the wreckage of its own birth almost immediately. And then there are the supernovae that never actually happen, at least not the way anyone expects. In certain cases, the collapsing core of a massive star may simply overwhelm the outward-moving shock wave entirely. Instead of rebounding and blasting the star apart, the shock loses its fight against gravity, and material simply continues falling inward until a black hole quietly forms, with no explosion at all. Astronomers have gone looking for these failed supernovae using a method that's almost charmingly simple. Photograph huge numbers of massive stars in nearby galaxies again and again over years, and watch for any of them to simply vanish, without ever producing the expected final flash. Several intriguing candidates have already turned up, including one enormous red supergiant that brightened only modestly before quietly fading out of view for good. If these silent deaths turn out to be common, they may finally explain a puzzle that had bothered astronomers for years. Why so many of the most massive stars appear to be missing from the census of ordinary supernovae, as though some of the universe's most dramatic deaths simply choose, for reasons still not fully understood, to happen in complete silence and darkness instead. Whatever remains after a successful core collapse supernova is one of the strangest objects the universe is capable of producing, a neutron star. To build one, take something more massive than our entire sun and compress it down until it's only about 20 kilometers across, roughly the size of a modest city. That's not a metaphor. That's the actual, physical scale of the compression involved. To understand just how extreme that is, it helps to remember that ordinary matter is mostly empty space. An atom's nucleus is tiny, and its electrons orbit at relatively enormous distances around it. Inside a collapsing stellar core, gravity becomes strong enough to crush that emptiness away entirely. Electrons are forced into protons, transforming them into neutrons, and the resulting material becomes packed at densities similar to the inside of an atomic nucleus itself, but stretched across an object many kilometers wide, rather than confined to a single, infinitesimally small point. A teaspoon of that material, just one ordinary teaspoon, would weigh something on the order of billions of tons here on Earth. Of course, it could never simply sit on a table. Outside the crushing gravity that holds a neutron star together, matter like that couldn't exist in that form at all. It would violently, catastrophically expand back towards something more ordinary. The surface gravity of a neutron star is almost impossible to translate into everyday experience. Drop an object near one, and it would accelerate downward with a force many times stronger than anything possible on Earth. And despite this staggering compression, a neutron star is still not a black hole. Light can still escape from its surface, which means astronomers can actually study its heat and its rotation directly. Neutron stars occupy a remarkable, narrow middle ground in nature, matter compressed just about as far as it possibly can be, without finally collapsing behind an event horizon and disappearing from the observable universe entirely. The outer layer of a neutron star, its crust, may be the strongest known material in existence. Deep inside it, nuclear forces trying to bind particles together are locked in an extreme tug-of-war with electrical repulsion trying to push them apart, and the resulting compromise is thought to be almost unimaginably rigid. Computer simulations suggest this crust may be something like 10 billion times stronger than steel, measured by how much strain it can withstand before finally breaking. That doesn't mean you could mine it and bring a sample home. Remove neutron star material from the crushing gravity that maintains it, and it would change catastrophically, instantly, into something else entirely. But while it remains in place, that extraordinary strength lets the crust support tiny distortions, imperfections that would be utterly invisible on a human scale, but that, attached to an object this massive and this dense, can have real astrophysical consequences, including the possibility of generating continuous gravitational waves as the star spins. And when astronomers say tiny, they mean it almost comically literally. What a physicist might casually call a mountain on a neutron star could rise only a few millimeters, maybe a couple of centimeters, above the average surface. On Earth, mountains rise for kilometers. On a neutron star, gravity is so overwhelming that even the strongest possible material can only support the faintest of bumps. And yet, because a neutron star packs more mass than our entire sun into such a small space, even a bump measured in millimeters represents an enormous quantity of displaced matter. If the star is spinning rapidly, that tiny irregularity can make its gravitational field very slightly with each rotation, in principle producing a continuous, faint stream of gravitational waves that detectors on Earth are actively trying to catch. Beneath that crust, the physics gets stranger still. At sufficiently low temperatures and under sufficiently extreme pressure, the neutrons inside a neutron star's interior are thought to pair up and form what's called a superfluid, a quantum state of matter that flows with essentially zero friction. This isn't purely theoretical. Physicists have created superfluids in laboratories on Earth, but only under extraordinarily cold, carefully controlled conditions. A neutron star provides a completely natural version, driven not by refrigeration, but by sheer, crushing density. This superfluid doesn't just swirl gently the way water might in a glass. Its rotation organizes itself into countless quantized vortices, threading through the star's interior, and how those vortices interact with the solid crust above them may explain one of the strangest behaviors observed in these objects. Every so often, a neutron star does something that seems to violate its own steady, predictable nature. Ordinarily, these stars slow their rotation very gradually over time, as they lose rotational energy. But occasionally, a neutron star's spin rate suddenly jumps, just slightly, faster instead. Astronomers call this a glitch. The leading explanation involves that hidden superfluid interior. As the solid crust slows down, some of those internal quantum vortices may stay temporarily pinned in place, refusing to slow down along with it, creating a growing mismatch between the rotation of the crust and the rotation of the fluid trapped beneath it. Eventually, enough of those vortices shift suddenly at once, transferring angular momentum outward and making the crust visibly, measurably speed up. It's one of the only ways scientists have to indirectly probe what's actually happening deep inside a neutron star's interior, a place no instrument will ever be able to physically reach. Just beneath the crust, in a thin transitional layer where the outer solid shell gives way to the exotic interior, matter may organize itself into structures physicists have, only half-jokingly, named after food. Here, nuclear forces trying to bind protons and neutrons together are locked in competition with electrical forces trying to push apart, and the resulting compromise doesn't necessarily produce neat, familiar, spherical nuclei. Simulations suggest it might instead produce long rods, flat sheets, and tangled, twisted shapes that researchers have nicknamed things like nuclear spaghetti and nuclear lasagna. The humor doesn't diminish the physics. This so-called nuclear pasta could be among the strongest, stiffest material configurations that exist anywhere in the universe, and its structure may influence how heat and magnetism move through a neutron star's crust, and even how matter behaves during the most violent moments of a neutron star collision. No one will ever collect a sample. All of this comes from theory and simulation, describing a layer of exotic matter sitting just beneath the surface of some of the densest objects the universe has ever built. Even the surface itself often isn't quite what it seems. Rather than solid crust facing empty space directly, a neutron star may hold a remarkably thin, but optically important, atmosphere above it, usually dominated by whichever light element, hydrogen or helium, happens to be present, since heavier elements tend to sink rapidly under such extreme gravity. That thin veil matters enormously to astronomers trying to interpret a neutron star's light, because different atmospheric compositions shape the outgoing radiation in very different ways, and getting it wrong can seriously distort estimates of the star's true temperature and size. A newborn neutron star begins its existence unimaginably hot, its interior briefly reaching temperatures of tens or even hundreds of billions of degrees. And yet it cools remarkably quickly, mostly by continuing to shed those same ghostly neutrinos we talked about earlier, particles that carry heat away from deep inside the star far more efficiently than ordinary light ever could. Over thousands of years, the surface temperature drops dramatically, though the star can remain hot enough to glow steadily in X-rays for a very long time afterward. By comparing a neutron star's measured temperature against its estimated age, astronomers can actually probe hidden physics occurring kilometers beneath a surface no instrument will ever directly touch. A dead star's fading heat becomes, in its own quiet way, a diagnostic tool for understanding matter under conditions no laboratory on Earth could ever hope to reproduce. Some neutron stars announce their existence in an entirely different way, not through slowly fading heat, but through an almost impossibly precise, rhythmic pulse of radio waves, sweeping across the galaxy like a lighthouse beam. These are called pulsars, and they were discovered almost by accident in the late 1960s, when radio astronomers noticed a signal repeating with such astonishing, mechanical regularity that some researchers briefly, half-seriously, wondered whether they might have stumbled onto an artificial transmission from an alien civilization. Nature, as it so often does, turned out to have a stranger and more elegant explanation. A pulsar is a rapidly rotating neutron star whose magnetic axis is tilted away from its axis of spin. Charged particles accelerate violently around its magnetic poles, producing narrow, tightly focused beams of radiation. As the star rotates, those beams sweep around like the light from a lighthouse. And if one happens to sweep across Earth during each rotation, our telescopes register it as a pulse, once per turn, with a regularity that can rival some of the best atomic clocks ever built. Today, thousands of pulsars are known, and their timing is precise enough that astronomers use them to test gravity itself, map invisible interstellar material, and hunt for planets orbiting stars that have already died. That regularity turns out to be extraordinarily useful. Astronomers can measure exactly when each individual pulse arrives at Earth and compare it against a detailed mathematical model of how it should behave if nothing were disturbing it. Tiny departures from that prediction can reveal remarkable things. A pulsar might be orbiting a hidden companion star, its timing subtly warping as gravity tugs it back and forth. It might be traveling through curved space-time in ways that let astronomers directly test general relativity. In one of the more delightful surprises in the history of astronomy, the very first confirmed planets outside our own solar system weren't found around an ordinary star at all. They were found around a pulsar, discovered because the neutron star's own gravity was being tugged back and forth, ever so slightly, by planets orbiting it, shifting its pulse timing by a measurable amount. Even the thin interstellar gas scattered between the stars leaves its fingerprint, since different radio frequencies travel through that ionized material at very slightly different speeds. Correcting for that delay gives astronomers a way to map material floating in the seemingly empty space between us and the pulsar itself. A signal that looks, on the surface, like nothing more than a simple, repetitive beat, ends up carrying an enormous amount of hidden information about everything it has passed through on its long journey to Earth. Some pulsars spin at speeds that strain belief. The fastest confirmed examples rotate more than 700 times every single second, a scale of rotation where the star's own surface moves through space at a genuinely significant fraction of the speed of light. These are called millisecond pulsars, since a single complete rotation takes only a few thousandths of a second. Curiously, many of them probably weren't born spinning this fast. Instead, they appear to have been spun up later in life, by slowly stealing gas from a companion star. As that stolen material spirals inward toward the neutron star, it transfers its own angular momentum onto the star's rotation, gradually accelerating it, recycling an older, slower pulsar into one of the most stable, rapid rotators in the entire universe. There's a physical limit to how fast this can go. Spin a neutron star too quickly, and material at its equator would simply no longer stay gravitationally bound to the surface at all, flying off into space. By measuring exactly how fast the fastest known pulsars actually spin, physicists can place real, meaningful constraints on the internal strength and structure of neutron star matter. using rotation speed itself as an experimental probe into physics no laboratory on Earth could otherwise access. Not every pulsar behaves with perfect, unbroken predictability. We already touched on the strange, sudden speed-ups called glitches, tiny hiccups in an otherwise impeccably steady rhythm, caused by that hidden superfluid interior briefly slipping against the solid crust above it. These glitches remain one of the only windows astronomers have into the deep, inaccessible interior of a neutron star, a place that will likely never be probed by any instrument more direct than the subtle timing of a distant radio pulse. Perhaps the most famous pulsar of all sits at the very center of that same Crab Nebula we talked about earlier, the visible remnant of the supernova recorded by Chinese astronomers back in the year 1054. The Crab pulsar spins around 30 times every single second, and each rotation sweeps a beam of radiation across space, producing pulses so regular that astronomers can monitor tiny, gradual changes in the star's rotation with extraordinary precision. Surrounding it lies a glowing nebula several light years across, continuously powered by a wind of energetic particles streaming outward from the spinning pulsar itself. Detailed images of the nebula reveal structures that visibly shift and change over surprisingly short timescales, including strange, moving wisps of material near the central star. It's a remarkable thing to sit with. The explosion that created this pulsar happened within recorded human history, nearly 1,000 years ago, and yet the collapsed stellar core left behind is still, right now, tonight, actively injecting fresh energy into the very debris field its own death created. There's also something quietly poetic buried in the discovery of a completely different kind of pulsar system, one found not through radio astronomy alone, but through decades of extraordinarily patient observation. In the 1970s, two astronomers, Russell Hulse and Joseph Taylor, discovered a pulsar locked into a tight binary orbit with another neutron star. Because the pulsar's radio signals were so precisely timed, researchers could track the pair's orbit with astonishing accuracy year after year. General relativity made a very specific prediction about a system like this. As the two neutron stars orbited each other, they should gradually lose energy by radiating gravitational waves, causing them to spiral closer together and complete each orbit ever so slightly faster over time. That's exactly what decades of careful observation revealed. The measured decay of the orbit matched Einstein's prediction with remarkable precision, long before any instrument on Earth had directly detected a gravitational wave passing through it. This discovery earned Hulse and Taylor the Nobel Prize, and it stands as one of the more beautiful examples in the history of science. Two collapsed, dead stars, quietly orbiting each other in the depths of the galaxy, ended up confirming one of the strangest predictions general relativity ever made, decades before humanity built anything capable of feeling that same invisible ripple directly. Among neutron stars, there exists a rare and genuinely extreme subgroup, objects whose magnetic fields are so intense that ordinary comparisons stop being useful entirely. These are called magnetars. Earth's own magnetic field is strong enough to guide a compass needle and help shield our planet from a steady stream of charged particles arriving from the sun. A magnetar's magnetic field can exceed that by trillions of times. Trillions, not thousands, not millions. At that intensity, the field becomes powerful enough to distort the actual structure of atoms near the star's surface, and to change how electrons themselves behave, stretching and rearranging matter in ways that simply don't happen anywhere else in the known universe. Exactly how a neutron star ends up becoming a magnetar, rather than an ordinary pulsar, remains an active area of research. One leading idea suggests that if the collapsing stellar core was spinning extremely fast at the moment of collapse, violent internal motions inside the newly forming neutron star could amplify its magnetic field enormously through a process similar to a dynamo, but operating under conditions vastly more intense than anything else in nature. Two massive stars, beginning their lives with broadly similar ingredients, might end up taking wildly different paths, one settling into an ordinary, well-behaved pulsar, the other becoming the most magnetic object known to exist. That magnetic field doesn't just sit there quietly. As it shifts and evolves over time, it can twist and strain the neutron star's rigid outer crust, the same extraordinarily strong material we talked about earlier. That crust may resist the growing stress for years, sometimes decades, before suddenly fracturing or shifting all at once, an event astronomers sometimes call a starquake. Unlike an earthquake here on Earth, this disturbance happens on an object whose gravity and magnetism dwarf anything in our entire solar system. The sudden rearrangement can accelerate enormous numbers of particles and release a burst of X-rays or gamma rays, sometimes lasting only a fraction of a second, sometimes, in far rarer cases, unleashing what's called a giant flare, releasing a genuinely staggering amount of energy in an instant. One of these giant flares gives us a particularly vivid way to grasp just how powerful these events really are. On December 27, 2004, an enormous pulse of gamma rays swept through our solar system, originating from a magnetar called SGR 1806-20, located tens of thousands of light years away, deep on the other side of the Milky Way. The initial fraction of a second was so intense that it briefly overwhelmed detectors on multiple spacecraft, instruments specifically designed to handle powerful cosmic events. And despite that enormous distance, the radiation reaching Earth was strong enough to measurably disturb our planet's ionosphere, the upper atmospheric layer that normally responds mainly to activity from our own sun. Had that same flare happened much closer to Earth, the consequences could have been genuinely severe. Instead, we received a harmless, but perfectly measurable, disturbance, a reminder that an object barely 20 kilometers across had briefly reached out across a significant fraction of our entire galaxy and gently, unmistakably touched the atmosphere above our heads. Magnetars, in a strange way, sit at the very edge of what stable matter can withstand, extraordinarily rare, extraordinarily brief in their most dramatic moments, and yet capable of announcing their existence across tens of thousands of light years, in the form of a single, sudden, violent rearrangement of a magnetic field too powerful for almost any other object in the universe to hold on to. Let's turn now to something even stranger than a magnetic flare crossing the galaxy: ripples in the actual fabric of space and time itself. When two black holes orbit one another, they do something no ordinary telescope could ever directly see. Their motion distorts the shape of space-time around them, and that distortion radiates outward in every direction at the speed of light as gravitational waves. At first, the two black holes might circle each other slowly, patiently, for millions or even billions of years. But as they radiate energy away through those very waves, their orbit gradually shrinks, and the process begins to accelerate. In the final moments before merger, everything speeds up dramatically. The two objects whirl around each other faster and faster, completing what might have taken years in just fractions of a second, until their event horizons finally touch, merge, and settle into a single, larger black hole. This final surge in frequency is often called a chirp, because if you convert the gravitational wave signal into sound, it genuinely sounds like a brief, rising chirp, sweeping upward in pitch before abruptly cutting off. The very first direct detection of this kind of signal was announced in 2016 from an event that had actually occurred in September of 2015. Two black holes, roughly 36 and 29 times the mass of our Sun, spiraling together and merging more than 1 billion light-years away. Nothing physically traveled from that collision to Earth in the way sound or ordinary matter would. Instead, the geometry of space itself changed, ever so slightly, as the wave passed through our planet, stretching and compressing distances by an amount smaller than the width of a single proton, measured across kilometer-long detector arms. And yet, remarkably, our instruments caught it. What makes this detection even stranger is where some of the mass actually went. The two original black holes carried a combined total of roughly 65 solar masses between them. The final merged black hole ended up with only about 62. The missing 3 suns worth of mass hadn't vanished, and it hadn't been blasted away as visible light, since the merger of two black holes produces essentially no light at all. Instead, that mass had been converted directly into gravitational wave energy, radiated outward as pure distortion in the shape of space-time itself. For a brief fraction of a second, during the most violent instant of the collision, the power being emitted in gravitational waves actually exceeded the combined light output of every star in the observable universe. Not because 3 suns worth of stars were destroyed, but because Einstein's own equation linking mass and energy allowed some of that already existing mass to be converted directly into a completely different form of radiation, one made of pure geometry rather than photons. Even after two black holes finish merging, the story isn't quite finished. The newly formed object doesn't simply relax immediately into a smooth, settled shape. Its horizon has just been violently distorted by the collision, and like a struck bell, it responds by oscillating in specific, characteristic patterns, radiating away those distortions as one final burst of gravitational waves, called a ring down. The comparison to a bell isn't just poetic. Just as a bell's exact tone depends on its shape and the material it's made from, a black hole's allowed vibration frequencies depend entirely on its own physical properties, specifically its mass and its spin. Careful measurement of these final, fading vibrations gives physicists an extraordinarily demanding test of general relativity itself, essentially a form of gravitational spectroscopy, identifying an object's properties not from the light it emits, but from the precise, fading pitch of space-time settling back into stillness after being violently disturbed. Strangely, the newly merged black hole doesn't always stay exactly where the collision took place. Gravitational waves carry not just energy, but momentum, and if a merger radiates that energy asymmetrically, more strongly in one direction than another, the resulting black hole has to recoil in the opposite direction to conserve that momentum, the same way a rifle kicks backward when it fires a bullet forward. This is called a gravitational recoil, or simply a kick, and simulations suggest that in some configurations, particularly when the two merging black holes have misaligned spins, this kick can send the newly formed black hole rocketing away at speeds of thousands of kilometers per second. In a small enough galaxy, a strong enough kick could be enough to eject the black hole from its host system entirely, sending it drifting alone through intergalactic space, carrying nothing with it but its own gravity and whatever tightly bound cluster of stars happen to be close enough to be dragged along for the ride. It's a genuinely strange image to sit with. Two invisible objects merge in near-total darkness, and the resulting collision can physically launch the survivor out of its own galaxy, like the recoil from an unimaginably enormous, silent, gravitational rifle. There's a completely different scale of gravitational wave hiding in the universe too, one far too slow and far too enormous for any laser-based detector on Earth to ever catch directly. When two entire galaxies merge, their central supermassive black holes can eventually find each other and settle into a binary orbit of their own, one that might take years or even decades to complete a single cycle. The resulting gravitational waves have wavelengths simply too vast for any Earth-based detector to measure. So astronomers had to get creative. They turned to millisecond pulsars scattered across our galaxy, using them as an enormous, natural array of extraordinarily precise clocks. If a slow-moving gravitational wave passes between Earth and one of these distant pulsars, it should very slightly alter the arrival time of its radio pulses. The effect on any single pulsar is far too small to notice on its own, but by monitoring dozens of pulsars scattered across the sky for years at a time, researchers can search for a very specific pattern of correlated timing changes, one that depends on the angular separation between each pair of pulsars in the sky. In recent years, several international collaborations have reported compelling evidence for exactly this kind of signal, not one single, sharp merger, but a persistent, low-frequency background hum, likely produced by the combined, overlapping gravitational waves from countless supermassive black hole pairs slowly spiraling toward each other across the entire universe. In effect, astronomers turned our own galaxy into a detector the size of the Milky Way itself, listening for a chorus of black hole pairs whose individual voices blur together into one continuous, ancient murmur. The gravitational wave story is still, in many ways, only just beginning. Ground-based detectors like the ones that made the first detection are limited in what frequencies they can actually hear, largely because the Earth itself is a noisy, vibrating place, and because their arms can only stretch so many kilometers before practical engineering limits take over. To listen for different, often larger and slower events, scientists are now designing detectors meant to operate far from Earth entirely. One ambitious mission concept involves 3 spacecraft flying in a precise triangular formation, separated not by kilometers, but by millions of kilometers of empty space, using laser beams to measure impossibly tiny changes in the distance between them. Freed from the Earth's constant seismic murmur, a detector like this could listen for entirely different kinds of gravitational waves, ones produced by merging supermassive black holes, and possibly even faint, ancient echoes left over from the earliest moments of the universe itself, signals no ground-based instrument could ever hope to catch. It's a strange kind of ambition, building an instrument sensitive enough to feel space-time itself trembling, and then flying it far from our own noisy, restless planet, just to listen more clearly. Black holes aren't the only compact objects capable of merging and shaking the universe. 2 neutron stars can do it too, and when they finally collide, they produce one of the most scientifically rich events astronomers have ever observed. Like a pair of merging black holes, 2 orbiting neutron stars gradually lose energy through gravitational radiation, spiraling closer and closer together over what can be billions of years before finishing, in their last moments, in a violent, rapid plunge toward each other. But unlike a black hole merger, this collision involves actual matter, unimaginably dense, neutron-rich matter, and when the 2 stars finally touch, that material gets thrown violently outward into space at extraordinary speed, under conditions rich enough in free neutrons to trigger exactly the kind of rapid neutron capture process we talked about earlier when discussing supernovae, only far more intensely. This is thought to be one of the universe's primary factories for many of the heaviest naturally occurring elements in the periodic table, including gold. Models built from observed collisions suggest that a single neutron-star merger might produce several times the mass of the entire Earth in freshly forged gold alone, along with a whole range of other heavy elements, including platinum and other precious metals. That material doesn't stay gathered together near the collision. It expands outward into interstellar space, eventually mixing into the gas clouds that will, much later, collapse to form entirely new stars and planetary systems. Which means the golden ring on someone's finger right now, tonight, might genuinely contain atoms forged not gently, inside the calm interior of a star, but violently, in the final, catastrophic instant when two collapsed stellar corpses finally collided. The visible aftermath of one of these mergers has its own name, a kilonova. It's far fainter than an ordinary supernova, but its changing color over time carries an enormous amount of information. The freshly created heavy nuclei are wildly unstable, and they begin decaying almost immediately. And that radioactive decay is what actually powers the glow astronomers observe. In the earliest hours, a kilonova can appear relatively blue. But as the ejected material expands and certain especially heavy elements, called lanthanides, begin to dominate its composition, the light shifts dramatically toward red and infrared wavelengths. Because those particular elements have complex atomic structures that make the debris far more opaque to visible light. By tracking exactly how that color evolves, night by night, astronomers can estimate what kinds of nuclei were actually produced in the collision and roughly how much material was thrown outward. All of this moved from theory to direct, dramatic confirmation on August 17, 2017. Gravitational wave observatories detected a signal unmistakably different from the earlier black hole mergers, one that lasted much longer and matched the predicted signature of two neutron stars spiraling together. Astronomers rapidly shared the estimated location with observatories all over the world, and within hours, telescopes located a genuinely new point of light in a galaxy called NGC 4993. Then, something remarkable happened. Nearly every major branch of observational astronomy converged on the same tiny patch of sky at once. Radio telescopes, optical instruments, X-ray observatories, all tracking different aspects of the same unfolding event. Less than 2 seconds after the gravitational wave signal itself, satellites had already recorded a short burst of gamma rays from the very same direction. For the very first time in the history of astronomy, gravitational waves and electromagnetic radiation had been used to study the exact same cosmic event simultaneously. This became known as GW 170817, and it marked the beginning of what astronomers call multi-messenger astronomy, using more than one entirely different physical messenger, space-time ripples and light, together to build a far more complete picture than either one could ever provide alone. Researchers used the observations to test the speed of gravity itself, to directly confirm heavy element production in real time, and to independently estimate the distance to a galaxy using a completely different method than astronomers had ever had access to before. One single collision, one instant, connected fields of physics that had mostly been working in isolation from one another for decades. What's left behind after a neutron-star merger isn't always the same. If the combined mass is simply too great for any neutron star to support, the remnant collapses almost immediately into a black hole. In other cases, rapid rotation may briefly help the merged object resist total collapse, surviving for milliseconds, seconds, or perhaps considerably longer, behaving for a short while. almost like a newborn magnetar, before finally succumbing to its own gravity. Each of these different outcomes shapes the surrounding explosion differently, and astronomers try to work out exactly which one happened in any given merger by carefully studying the combination of gravitational waves, gamma rays, and the fading light that follows. In effect, every single neutron star merger becomes its own natural experiment, testing precisely how much mass ultra-dense neutron star matter can withstand before gravity finally, decisively, wins. There's one more category of extreme event closely tied to both exploding stars and colliding neutron stars, and it may be the single most energetic phenomenon the universe is capable of producing in a short burst: the gamma-ray burst. The most powerful of these flashes can release, within a matter of seconds, an amount of energy that rivals or even exceeds everything our own sun will radiate across its entire 10 billion year lifetime, especially once astronomers account for how tightly that energy is actually focused. These are not simply ordinary stellar explosions viewed from unusually far away. They're highly concentrated events, associated either with the collapse of certain massive, rapidly rotating stars, or with the violent merger of compact objects like neutron stars. In both cases, much of the burst's radiation emerges through extraordinarily narrow, focused jets of material, moving at speeds astonishingly close to the speed of light itself. If one of those jets happens to point directly at Earth, even an explosion happening billions of light years away can appear spectacularly, almost impossibly bright in our sky. The burst itself can be over before a telescope even has time to turn and look, which is why automated spacecraft now watch the entire sky continuously, ready to send out alerts within moments of detecting anything unusual. Astronomers generally divide these bursts into two broad families, based mostly on how long they last. Long gamma-ray bursts, typically lasting more than about 2 seconds, are usually linked to the deaths of certain massive stars, ones that collapse in a way that manages to launch a narrow, relativistic jet straight through the surrounding stellar material before the star has even finished falling apart. Not every massive stellar collapse manages this. Something unusually powerful has to happen at the very center, along with just the right rotation and internal structure for the jet to successfully punch its way out. Short gamma-ray bursts, by contrast, usually last less than 2 seconds, and for decades, they were genuinely mysterious, since they often occurred far from any obvious region of active star formation. That pattern eventually pointed astronomers toward an entirely different origin: the merger of two compact objects, especially two neutron stars, systems that might survive, quietly orbiting each other for millions or billions of years, drifting far from where their original stars were even born, before finally colliding and releasing their entire remaining energy in a burst lasting less time than it takes to say a single sentence out loud. One crucial detail changes almost everything about how these events actually appear from Earth. Their radiation isn't spread evenly in every direction. It's concentrated into narrow jets, and because relativity dramatically amplifies radiation moving almost directly toward an observer, a burst can appear extraordinarily bright if its jet happens to point our way, or almost completely unnoticeable if it points anywhere else, even if the underlying explosion, geometrically speaking, was every bit as powerful. This creates a significant, systematic bias in what astronomers actually detect. Every burst we do observe represents only a small fraction of the true, much larger population happening throughout the universe, most of which simply never happen to aim their narrow beam of light in our particular direction. When a jet's initial burst of gamma rays finally fades, usually within seconds, the story is still far from over. The relativistic outflow eventually slams into surrounding interstellar gas, driving a shock wave that accelerates charged particles and generates radiation across the entire electromagnetic spectrum, an afterglow that can remain detectable at progressively longer wavelengths for days, weeks, sometimes even months after the initial flash. This afterglow often reveals far more scientific information than the brief burst itself. Its spectrum can reveal the event's true distance, and its slowly changing brightness can expose the jet's actual shape and the density of the material surrounding it. One particular burst deserves special mention, simply because of how genuinely extreme it was. On October 9, 2022, satellites detected an event so overwhelmingly bright that astronomers, only half-jokingly, nicknamed it the Boat, short for the brightest of all time. Its gamma radiation was intense enough to briefly saturate detectors specifically engineered to withstand powerful cosmic events, and even instruments never designed for gamma-ray astronomy at all noticed measurable effects. The burst originated billions of light-years away, but its narrow jet happened to be pointed almost exactly toward Earth, an alignment so favorable that it dramatically amplified how bright the event appeared from our particular vantage point. Researchers studying it across the electromagnetic spectrum eventually linked it to the collapse of a massive star, and remarkably, its radiation was strong enough to measurably disturb Earth's ionosphere, despite originating from a source so distant that its light had been traveling toward us for far longer than our own species has existed. Gamma-ray bursts also serve an entirely different scientific purpose, almost as a byproduct of how extreme they are. Because they can briefly outshine their entire host galaxy by an enormous factor, they act like a brief, extraordinarily powerful searchlight, shining through gas that would otherwise be nearly impossible to study directly. As a burst's afterglow passes through intervening material on its way to Earth, atoms in that material absorb very specific wavelengths of the light, leaving a kind of fingerprint that astronomers can read once the light finally reaches our telescopes. Some of the most distant confirmed bursts correspond to light that began traveling more than 13 billion years ago, from an era when the very first generations of stars and galaxies were still forming. Unlike other bright, long-lived objects, a gamma-ray burst doesn't remain active for millions of years, which means it probes the environment around a single, specific, dying star, rather than blending together information from an entire active galactic region. For a few brief minutes, the violent death of one remote, ancient star can backlight billions of years of otherwise invisible cosmic history, letting astronomers study material that would, under almost any other circumstance, remain completely dark and completely unreachable. Let's turn now to black holes themselves, and to one of the strangest, most gruesomely named phenomena in all of astrophysics, the tidal disruption event. A star doesn't actually need to cross a black hole's event horizon to be destroyed. If it simply passes close enough, the difference in gravitational pull between the side of the star facing the black hole and the side facing away can become overwhelming, stronger than the star's own gravity can resist. Those tidal forces stretch the star relentlessly until it can no longer hold itself together as a coherent, spherical object at all. Instead of falling inward whole, the star is pulled apart into a long, elongated stream of impossibly hot gas, a process astronomers have nicknamed spaghettification, though the more precise term is simply tidal disruption. Some of that stretched material escapes outward on long, unbound trajectories, never to return. The rest swings back around the black hole and begins forming a rapidly rotating disk of infalling debris. As that gas collides with itself and heats up, it can release an enormous burst of radiation, one bright enough to make a previously dark, dormant galactic center suddenly, unexpectedly flare to life. This gives astronomers a remarkable tool. Most galaxies harbor a supermassive black hole at their center, but if very little gas is actively falling into it, that black hole can remain essentially invisible, sitting in near-total darkness for centuries or far longer. The black hole itself never becomes visible, not even during a tidal disruption. What astronomers actually see is the destruction happening around it, the shredded star, glowing brightly as it's torn apart and consumed. By studying that flare, researchers can investigate black holes that might otherwise reveal almost nothing about their presence at all, using an unlucky wandering star as an accidental beacon, announcing the existence of an otherwise completely hidden gravitational giant. Being torn apart, remarkably, doesn't necessarily mean being entirely consumed. During disruption, different portions of the same star end up on wildly different trajectories, some more tightly bound to the black hole, destined to eventually fall back and feed it, and some flung outward with enough energy to escape entirely, disappearing into the wider galaxy, carrying with them material that once belonged to the star's deep interior. In certain rare cases, a star might not be destroyed completely at all on its first encounter. It could lose only its outer layers during a partial disruption, then swing away on a long, elongated orbit, only to return years or decades later for another close pass, and another partial stripping, again and again, until either it's eventually destroyed completely, or its structure changes enough that the entire pattern shifts. Astronomers have begun identifying exactly these kinds of repeating flares, and their regular timing offers something genuinely rare in this field. Instead of witnessing a catastrophe just once, researchers can watch the very same doomed star return to danger again and again on a schedule. Not every black hole behaves the same way when it comes to tidal disruption, and the reason has to do with a genuinely counterintuitive fact about how black holes scale with mass. For a relatively small, stellar mass black hole, the event horizon itself is quite compact, which means gravity changes extremely rapidly across any reasonably sized object nearby. Tidal force is strong enough to violently destroy an approaching star well before it ever reaches the horizon itself. But for a supermassive black hole, one containing millions or even billions of times the mass of our Sun, the horizon is vastly larger, and the gravitational gradient near that boundary can actually be far gentler by comparison. In fact, above a certain black hole mass, an ordinary Sun-like star could, in principle, cross the event horizon almost entirely intact, with any subsequent destruction happening only after it's already fallen somewhere light can never escape from again, hidden forever from outside observation. This means that, strangely enough, making a black hole even more massive can actually make visible tidal disruption less likely, not more, simply because its horizon eventually grows large enough to swallow stars whole before gravity has the chance to visibly tear them apart on the outside. There's an even stranger, more exotic version of this phenomenon involving objects that shouldn't normally be vulnerable to it at all. A white dwarf is so extraordinarily compact that an ordinary supermassive black hole would typically swallow it completely intact, long before tidal forces could ever manage to tear it apart. But something called an intermediate mass black hole, occupying the mysterious gap between ordinary stellar mass black holes and the giants found at galactic centers, changes that calculation entirely. If a white dwarf encounters a black hole in exactly that intermediate range, the tidal radius can lie safely outside the event horizon, meaning the compact star could actually be pulled apart before crossing the point of no return. In some scenarios, that violent compression might even trigger sudden, explosive nuclear burning inside the disrupted white dwarf, producing an unusual explosive transient unlike anything else in astronomy. Confirming such an event would be genuinely exciting for an entirely separate reason too, since intermediate mass black holes have proven remarkably difficult for astronomers to confirm directly. A disrupted white dwarf could become one of the clearest available signs that these elusive, in-between black holes actually exist at all. A small number of tidal disruption events do something even more dramatic than simply glowing brightly. They launch narrow, relativistic jets directly from the galactic center, in almost exactly the same way certain gamma-ray bursts do. One famous example, discovered in 2011 and named Swift J 1644+57, erupted violently in X-rays and remained wildly variable for an extended period. The leading explanation is a star being disrupted by a massive black hole, while a narrow jet happened to be aimed almost directly at Earth. Because relativistic beaming so dramatically enhances a jet viewed nearly head-on, only a small fraction of these jetted disruptions are ever likely to appear spectacular from our particular vantage point. In these rare, extreme events, two of the most violent processes in astrophysics happen simultaneously. One star, torn completely apart by gravity, and some fraction of the energy released by its own destruction, immediately channeled into a narrow beam of matter moving at nearly the speed of light. Let's zoom out now, from single stars and single black holes, to something far larger in scale. Entire galaxies colliding with one another. It's tempting to picture a galactic collision as an almost unimaginable demolition derby. Billions of stars smashing violently into billions of other stars. In reality, that's almost never what happens. Galaxies are mostly empty space. Even in their densest, most crowded regions, the distances between individual stars are so enormous compared to the stars themselves that when two galaxies pass through one another, the vast majority of their stars simply continue along altered paths without ever physically touching. Gravity does the real damage here, not direct collision. Each galaxy pulls on the other, gradually reshaping the orbits of countless stars at once. Some stars get pushed onto wider paths. Others get flung outward into long, sweeping streams that can extend for hundreds of thousands of light years beyond either original galaxy. Gas behaves very differently, though, unlike stars, interstellar gas clouds genuinely can and do collide, compress, and shock as two galaxies overlap, driving huge amounts of raw material inward, often fueling intense new bursts of star formation in the process. A galactic collision can therefore look absolutely, chaotically violent from a distance: tangled arms, distorted shapes, sweeping tidal tails, while at the level of individual stars, the actual participants almost never come remotely close to touching one another. That gravitational reshaping can transform a galaxy's appearance almost completely. A spiral galaxy doesn't necessarily keep its elegant, pinwheeling shape forever. When another galaxy approaches, its gravity can pull strongly on the disk, stretching, bending, or dramatically amplifying its spiral arms. Closed passages can draw broad bridges of stars and gas directly between the two galaxies, while other material gets flung outward into sweeping structures that can remain visible for a very long time after the closest approach has already passed. The entire process unfolds slowly by any human measure of time, often across hundreds of millions of years, with galaxies sometimes passing directly through one another more than once before finally settling into a single, merged system. Our own galaxy carries a quiet record of exactly this kind of ongoing process. Smaller satellite galaxies orbit the Milky Way, and some are gradually being pulled apart by its gravity as we speak. The Sagittarius dwarf galaxy is a striking example, repeatedly passing close to the Milky Way and having stars continuously stripped away, stretched into enormous streams that wrap through the galactic halo surrounding us. Astronomers can identify these former members of a now-vanishing galaxy by carefully measuring their motion and their chemical composition, distinguishing them from stars that formed natively within the Milky Way itself. This slow, ongoing process is sometimes called galactic cannibalism, even though it happens entirely through gravity rather than anything resembling actual consumption. The smaller galaxy gradually loses its own identity, its stars slowly folding into the larger system until the boundary between ours and theirs essentially disappears. Some of the stars near our own solar system, right now, may well have been born inside a completely different galaxy, long before being gravitationally absorbed into the Milky Way. And our galaxy has a collision of its own still ahead of it. The nearby Andromeda galaxy, our largest neighboring spiral, isn't drifting away from us the way most distant galaxies are, carried along by the overall expansion of the universe. It's actually approaching, gravitationally bound to the Milky Way, and current measurements suggest the two galaxies are on a course that will eventually bring them together several billion years from now. The exact sequence of events remains somewhat uncertain, since even tiny differences in sideways motion can meaningfully change how the encounter unfolds. But most models predict at least one close, dramatic passage, followed eventually by a slow, gradual merger into one much larger galaxy. Individual stars, including our own Sun, likely wouldn't be directly endangered by physical collisions during this process, for exactly the same reason ordinary galactic mergers rarely involve stars actually touching. But the overall structure of both galaxies would be reshaped dramatically, their disks distorted almost beyond recognition before eventually settling into something new entirely. It's a strange thing to consider on a quiet night like this one. The Milky Way, the galaxy holding everything you've ever known, has its own future already written into the physics of gravity, a future that includes merging with another galaxy every bit as vast as our own. When galaxies do collide, one of the most dramatic consequences is what happens to their gas, rather than their stars. Interstellar gas clouds occupy a much greater share of a galaxy's available space than stars do, which means when two galactic disks pass through one another, huge clouds of gas genuinely can and do collide directly, creating shocks that heat some material and compress other regions into extraordinarily dense layers. That compressed gas can lose orbital energy more efficiently than stars, sinking inward toward the center of the merging system, sometimes triggering an intense burst of new star formation, sometimes feeding a central black hole instead. Astronomers call these especially intense bursts of new star creation starbursts, and some interacting galaxies form new stars at rates far beyond anything seen in a calm, undisturbed spiral galaxy. One particularly dramatic example, sometimes called the antennae galaxies, currently displays enormous clusters of brand new stars, some individual clusters containing many thousands, occasionally millions, of newborn stars, all forged from gas compressed and rearranged during an ongoing galactic collision. A collision that looks destructive on the grandest possible scale can, at exactly the same time, be one of the most productive periods in either galaxy's entire history. Some of the most spectacular structures created by these encounters extend far beyond the visible boundaries of either original galaxy. During a close passage, Gravity pulls more strongly on the near side of each galaxy than the far side, stretching material outward into enormous tidal tails, structures that can extend for hundreds of thousands of light years, containing stars that once belonged securely to each galactic disk, along with gas dragged outward during the same encounter. In rare cases, enough of that displaced debris can gather itself, under its own gravity, into an entirely new, self-bound structure called a tidal dwarf galaxy, a genuinely new galaxy, born not from primordial material left over from the early universe, but from the wreckage of two older, more mature galaxies colliding. It's one of the stranger reminders that galaxies are not fixed, finished objects. They are constantly, slowly being reshaped, torn apart, and occasionally, quietly, reborn. Even the black holes at each galaxy's center eventually join this process. When two large galaxies merge, each brings its own central black hole along with it, and over time, gravity draws those two black holes together as well, first into a wide, slow binary orbit, and eventually, after enough time has passed, potentially into a merger of their own, radiating gravitational waves across a scale so enormous that we can only currently detect their combined, distant murmur rather than any single, individual event. Direct collisions between individual stars, as opposed to entire galaxies, are almost unheard of across most of a galaxy's ordinary volume, simply because stars are so small compared to the enormous distances separating them. But the situation changes dramatically inside the crowded cores of dense star clusters, where thousands, sometimes millions, of stars can occupy a surprisingly small volume of space, continually passing near one another on tangled, complicated orbits over billions of years. In these exceptionally crowded environments, chance encounters can occasionally bring two stars close enough to genuinely touch or merge outright, gravity itself acting to focus and increase the likelihood of these encounters over time. The result can be a star that appears, by every conventional measure, younger and hotter than it has any right to be, given the age of the surrounding cluster. Astronomers call these blue stragglers, stars that seem to have defied the normal aging process entirely, most likely because they were formed or substantially reinvigorated through a stellar merger or a close gravitational interaction with a companion. Because both stars involved in such a collision are made of flowing, gaseous material rather than rigid, solid surfaces, computer simulations show the encounter stripping, shocking, and thoroughly mixing material from both stars during the collision itself, producing a genuinely new object, forged from the wreckage of two older ones. Most stars, across their entire lifetimes, will never come anywhere close to touching another star. But in the very densest, most crowded pockets of the cosmos, that near-impossible event becomes, over long enough timescales, an ordinary and important part of how some stars actually evolve. Let's slow down for a moment. If your thoughts have started to blur a little, that's exactly right. That's exactly what these long, quiet science journeys are for. You don't need to hold on to every number, every name, every explosion. Just let the shapes of these ideas wash over you gently. Dying stars, ancient light, ripples in space too small to imagine, and let your body keep doing what it already knows how to do. We still have a little more to explore tonight, some strange radio flashes from across the universe, and some of the most colossal, ancient objects ever discovered. There's no need to follow every word closely. Just stay here, resting, and let the rest of tonight's journey carry you the remaining distance. There's a category of extreme cosmic event that remains, even now, only partly understood, and it involves some of the briefest, most energetic flashes of radio waves ever detected, fast radio bursts. These events last only a few thousandths of a second, and yet, in that impossibly brief span, they can release as much energy as our sun produces over an entire day, sometimes considerably more. Astronomers first identified them in archived data in 2007, and for years afterward, nobody was entirely sure whether they were even real or simply some strange instrumental glitch, since so few had actually been observed. That changed as radio telescopes improved, and thousands of these bursts have now been detected, arriving from galaxies scattered across billions of light years of the observable universe. What actually produces a burst this brief and this powerful remains a genuinely open question, though the evidence increasingly points toward magnetars, those same extraordinarily magnetized neutron stars we explored earlier. In 2020, astronomers caught an especially exciting piece of evidence, a fast radio burst originating from within our own galaxy, traced directly back to a known magnetar. That single detection gave researchers real confidence that at least some of these bursts come from exactly the kind of violent magnetic rearrangement that also produces the giant flares we discussed, just scaled and observed at radio wavelengths instead. But not every fast radio burst behaves the same way. Some flash only once and are never seen again. Others repeat, sometimes on a strange, semi-regular schedule that stretches across days or weeks, hinting that whatever produces them might be embedded in a binary system, or perhaps orbiting some other object that periodically enables or blocks the emission. A handful of especially active repeating sources have released hundreds of individual bursts within just a few hours, suggesting that whatever central engine is producing them can somehow reset itself remarkably quickly over and over again, without being destroyed in the process. Because these bursts are so brief and so bright, they've become an unexpectedly useful tool for an entirely different purpose: mapping the invisible matter scattered throughout the universe. As a burst radio waves travel across intergalactic space, they pass through faint, diffuse gas that would otherwise be almost impossible to detect directly, gas so thin and so widely spread out that ordinary telescopes struggle to see it at all. That gas subtly delays different radio frequencies within the burst by very slightly different amounts, an effect that grows stronger the farther the burst has traveled. By carefully measuring that delay, astronomers can estimate the total amount of ordinary matter the burst has passed through on its way to Earth, giving them, almost by accident, a working census of matter distributed across the universe, matter too faint and too diffuse to be counted through almost any other method available. A signal lasting less than the blink of an eye has become one of astronomy's more unlikely tools for measuring the universe on its very largest scales. There's a completely different, far more violent kind of collision worth pausing on too, one that doesn't happen between entire stars, but between individual, subatomic particles, moving at speeds close enough to light that ordinary physics starts behaving in genuinely strange ways. Cosmic rays, high-energy particles accelerated by some of the most violent processes in the universe, supernova remnants, active black holes, and possibly sources we haven't fully identified yet, constantly rain down on Earth's atmosphere. When one of these particles strikes an atom high above us, it can trigger an entire cascading shower of secondary particles, muons and short-lived, unstable hadrons, raining down toward the ground before decaying away into lighter, more familiar particles within fractions of a second. Most cosmic rays carry relatively modest energies, but every so often, something far stranger arrives. In 1991, a detector in Utah registered a single particle carrying an energy so extreme that physicists nicknamed it, only half-jokingly, the "oh my god" particle. Its energy was comparable to a well-thrown baseball, but concentrated into a single subatomic particle, something so far beyond ordinary cosmic ray energies that astronomers still aren't entirely certain what process in the universe could have accelerated it. Whatever cosmic engine produced that single particle remains, even now, a genuine open mystery, a tiny, nearly massless traveler carrying an almost unreasonable amount of energy across unimaginable distances before ending its journey, quietly, in the upper atmosphere above the Utah desert. Environments this extreme can, in principle, briefly recreate conditions unlike anything else accessible to physicists on Earth, conditions violent enough that familiar particles can transform into unusual, extremely short-lived states that don't normally exist anywhere in the ordinary universe around us. Researchers studying neutron star mergers and the ultra-energetic jets launched by certain black holes are essentially watching nature run particle physics experiments at scales and energies no human-built laboratory could ever hope to reproduce. Some scientists even wonder whether such extreme environments might eventually help explain long-standing mysteries like dark matter, the invisible, unidentified substance that appears to outweigh all of the ordinary, visible matter in the universe several times over. No confirmed astrophysical collision has yet revealed a genuinely new fundamental particle. But the appeal of these environments is obvious. Nature, in its most violent moments, reaches energies and conditions simply unavailable anywhere else, turning the universe's most extreme catastrophes into experiments it performs entirely on its own, with the results occasionally drifting down to Earth for us to study, quietly, decades or centuries after the fact. Let's turn now to some of the most persistently powerful objects in the entire universe, ones that don't simply flare briefly and fade, but can remain extraordinarily active for millions of years at a stretch: quasars, and the broader family of active galactic nuclei they belong to. At the center of many galaxies sits a supermassive black hole, sometimes containing millions, occasionally billions, of times the mass of our Sun. Most of the time, as we discussed earlier, these black holes sit quietly, with little gas actively falling inward, giving off almost no detectable radiation at all. But under the right conditions, when a steady supply of gas is available, that black hole can become extraordinarily active, and the results are almost impossible to overstate. As matter spirals inward, it forms a hot, rapidly rotating accretion disk, and the friction and compression within that disk can heat the infalling gas to millions of degrees, causing it to radiate enormous amounts of energy across nearly the entire electromagnetic spectrum: radio waves, visible light, ultraviolet, X-rays, sometimes gamma rays as well. In the most extreme cases, this glowing disk alone can outshine every single star in the black hole's entire host galaxy combined, a small region, not much larger than our solar system, outperforming the combined light of hundreds of billions of ordinary stars. The earliest examples of these objects, discovered in the 1960s, were genuinely baffling to astronomers at the time. They appeared, through early telescopes, to be nothing more than ordinary, faint, star-like points of light. But their spectra revealed something impossible for an ordinary star. Light shifted dramatically toward longer wavelengths, indicating enormous distances so vast that whatever was producing that light had to be almost inconceivably powerful to still appear detectable from Earth at all. Astronomers coined the term quasar, short for quasi-stellar radio source, to describe these mysterious, compact, unbelievably luminous objects, and it would take years of further research before the picture we understand today, a supermassive black hole actively feasting on infalling gas, finally came into focus. Many active galactic nuclei also launch narrow, powerful jets of material, similar in principle to the jets produced during certain gamma-ray bursts and tidal disruption events, but sustained continuously, sometimes for millions of years at a time, rather than flaring briefly and fading. These jets, threaded and powered by intense magnetic fields anchored near the black hole itself, can extend for hundreds of thousands, occasionally millions, of light years beyond their host galaxy. Some of the largest coherent structures in the entire universe, built and maintained by an object that, by cosmic standards, is genuinely tiny. When one of these jets happens to point almost directly at Earth, relativistic beaming, the same effect that made certain gamma-ray bursts and disrupted stars appear so dramatically bright, can make the entire system appear extraordinarily powerful, a category astronomers call blazars, some of the most persistently luminous individual objects observable anywhere in the sky. Quasars, remarkably, weren't just an early universe curiosity. Astronomers have found that they were actually far more common billions of years ago than they are today, an era sometimes informally called cosmic noon, when galaxies generally contain more available gas, and supermassive black holes had correspondingly more fuel available to power this kind of dramatic activity. As that available gas gets consumed, or expelled outward through violent feedback from the black hole's own radiation and jets, galaxies tend to quiet down over time, their central black holes gradually settling into the more dormant state we see in most galaxies, including our own, today. In a sense, studying distant quasars means looking directly back into an earlier, more energetic chapter of the universe's history, an era when galactic centers routinely blazed with a violence that's grown considerably rarer in the calmer universe we happen to inhabit now. There's also a strange kind of self-regulation buried inside this whole process. As a quasar's central black hole grows more and more active, the sheer radiation pressure and energetic outflows it generates can begin pushing surrounding gas away from the galaxy entirely, effectively starving the very black hole that produced them of its own future fuel supply. Astronomers refer to this as feedback, and it appears to play a genuinely important role in regulating how large galaxies, and the black holes at their centers, actually grow over cosmic time. In other words, some of the most violent, luminous objects in the universe may also be quietly enforcing their own limits, throttling their future growth simply by being as energetic as they currently are. Sometimes, an extreme cosmic event doesn't announce itself through its own light at all, but by bending and distorting the light of something else, something positioned far behind it. Massive objects, whether individual galaxies, entire galaxy clusters, or black holes, warp the shape of space-time around them, exactly as general relativity predicts, and light passing close to that warped region gets bent along a curved path, rather than traveling in a perfectly straight line. This phenomenon is called gravitational lensing, and it turns some of the universe's most massive structures into accidental telescopes, once far more powerful than anything humanity could ever hope to build directly. When a massive galaxy cluster sits directly between Earth and some more distant background galaxy, its gravity can bend and magnify that distant galaxy's faint light, sometimes stretching it into long, curved arcs, sometimes splitting a single distant object into multiple separate images, all appearing simultaneously around the lensing cluster. Astronomers have used this effect to study galaxies so distant and so intrinsically faint that they would be completely invisible without this fortunate cosmic magnification. In certain especially precise alignments, when the background source, the lensing object, and Earth all line up almost perfectly, the distant light can be bent into a complete or near-complete ring encircling the foreground object entirely. A striking configuration astronomers call an Einstein ring, named, naturally enough, after the physicist whose equations first predicted the effect. These alignments are relatively rare, and finding one is often as much about luck as it is about careful searching, but each one provides an extraordinarily precise natural laboratory for testing exactly how gravity bends light under real, astrophysical conditions, rather than relying purely on theoretical calculation. Gravitational lensing has also become one of astronomy's most powerful indirect tools for studying dark matter, that invisible, unidentified substance that appears to make up roughly 5 times as much of the universe's total mass as all the ordinary, visible matter combined. Dark matter doesn't emit or absorb light, which means it can't be observed directly through any conventional telescope. But it does have gravity, and that gravity bends light exactly as ordinary mass would. By carefully mapping exactly how background galaxies get distorted and magnified around a foreground cluster, astronomers can effectively map out the total gravitational mass of that cluster, including the invisible portion, revealing where dark matter is actually concentrated, even though it can never be seen directly, only inferred from its gravitational influence on the light passing near it. In some of the most dramatic cases, astronomers have even watched colliding galaxy clusters where the visible, ordinary gas gets slowed and displaced by the collision itself, while the lensing signal, tracing the underlying dark matter, sails straight through largely undisturbed, offering some of the most compelling direct evidence that dark matter genuinely behaves differently from ordinary matter, interacting through gravity, but almost nothing else. Even individual, relatively small objects can produce a brief, temporary version of this same effect. When one star happens to pass almost directly in front of another, more distant star, from Earth's particular vantage point, the nearer star's gravity can very briefly magnify the light of the star behind it, an effect called microlensing. Because it depends entirely on a chance, temporary alignment, rather than a fixed, permanent structure, each microlensing event is a genuinely unrepeatable occurrence, a brief brightening that rises and fades over days or weeks, and then never happens again in quite the same way. Remarkably, this technique has even been used to detect planets orbiting distant stars, since a planet's own gravity can subtly distort the pattern of brightening in a way large enough for careful observers to notice, revealing entire distant solar systems through nothing more than a fleeting, temporary bending of light that will likely never be observed again. Earlier tonight, we talked about how a merging pair of stellar mass black holes can recoil violently enough, in some configurations, to be kicked entirely out of a small galaxy. It turns out the same basic physics can apply on a far grander scale, to the supermassive black holes sitting at the very centers of merging galaxies. When two galaxies fully merge, their central black holes eventually spiral together and collide, just as we discussed earlier, and if that final merger happens to be sufficiently asymmetric in mass, in spin, or in the geometry of the collision itself, the resulting gravitational recoil can be enormous, potentially launching the newly merged black hole clean out of the combined galaxy's core entirely. If the kick isn't quite strong enough for a full ejection, the black hole may instead begin a long, slow journey outward through its own galaxy, drifting thousands of light years from the center before gravity gradually pulls it back, losing energy through repeated interactions with surrounding stars and gas, and eventually settling back down, sometimes over a timescale of hundreds of millions of years. During that wandering phase, the displaced black hole might drag along a small, tightly bound cluster of stars, or a modest trail of accreting gas, either of which could make an otherwise invisible, isolated black hole detectable to careful observers. Astronomers have begun searching for exactly this kind of evidence: unusual, off-center clusters, or active black holes sitting suspiciously far from the geometric center of their host galaxy. And while confirmed examples remain difficult to pin down conclusively, the underlying physics is a striking reminder that galactic nuclei aren't always the calm, orderly, perfectly centered places we tend to picture. A black hole spends its entire early history sitting exactly where a galaxy formed it. And then, in one single violent merger, it can be sent wandering, alone, through its own galaxy or beyond it entirely, carrying nothing with it but its own gravity and whatever else happened to be close enough to be pulled along for the ride. There's one more category of extreme cosmic history worth mentioning before we bring tonight's journey to a close, one written not in modern telescope data, but in centuries-old records made by careful observers who had no concept of what they were actually witnessing. In the year 1006, observers across China, Japan, the Islamic world, and parts of Europe recorded an extraordinarily bright new star appearing in the southern sky, one that, by several historical accounts, may have briefly rivaled the brightness of the moon itself and remained visible, at least faintly, for the better part of 2 years. Modern astronomers have connected this event to what's now called SN 1006, believed to be the brightest supernova ever recorded in human history, a thermonuclear explosion of exactly the white dwarf variety we discussed earlier, occurring only a few thousand light years from Earth, close enough to genuinely dominate the night sky, but comfortably far enough away to leave absolutely no lasting harm to anyone here. Astronomers have since located its expanding remnant, a huge, faint shell of debris still visibly expanding outward, nearly 1,000 years after the original explosion, giving researchers a rare, well-documented historical anchor point for studying exactly how these particular thermonuclear explosions evolve over very long timescales. And finally, there's one more category of extreme object worth sitting with for a moment, one that has never actually been confirmed to exist, but that remains a genuinely serious subject of ongoing research: primordial black holes. Unlike every black hole we've discussed tonight, all formed from the collapse of dying stars or the merger of existing compact objects, a primordial black hole, if such a thing exists, would have formed almost immediately after the universe itself began, born not from a collapsing star, but from extraordinarily dense regions in the very early, turbulent universe collapsing directly under their own gravity, long before any stars had even formed. These hypothetical objects could, in principle, span an enormous range of sizes, some potentially smaller than a single atom, yet carrying the mass of a mountain, others potentially rivaling the mass of an entire star. Some researchers have even proposed that primordial black holes, if they exist in sufficient numbers, might help explain some or all of the universe's missing dark matter. No confirmed example has ever been found, but the search itself, scanning the sky for the extraordinarily subtle gravitational lensing signature such an object would produce, or waiting patiently for the fading final flash of one evaporating through a slow quantum process called Hawking radiation, remains one of the more genuinely open frontiers in modern astrophysics. A reminder that even after everything we've explored tonight, the universe may still be quietly holding on to entire categories of extreme objects that nobody has confirmed yet, patiently waiting to be found. Not every dramatic gravitational encounter ends with destruction. Sometimes, a star survives an extreme brush with a black hole's gravity, but gets launched away from it at a genuinely staggering speed. These are called hypervelocity stars, and the mechanism behind them is almost elegant in its simplicity. If a binary pair of stars wanders too close to a supermassive black hole, the black hole's gravity can capture one star into a tight orbit, while flinging its former companion outward with such enormous velocity that it can actually exceed the escape velocity of the entire galaxy. Astronomers have identified numerous stars racing outward from the direction of our own galaxy's center at speeds well over 1,000 kilometers per second, fast enough that, given enough time, they'll eventually leave the Milky Way entirely, sailing outward into the vast, mostly empty space between galaxies, alone, for the remainder of their existence. Tracing a hypervelocity star's trajectory backward can reveal, with real precision, exactly where and when it was launched, giving astronomers a way to study violent encounters near our galaxy's central black hole that happened long before any telescope was ever pointed in that direction. It's a strange kind of stellar exile. A star, once part of an ordinary binary system, suddenly finds itself flung entirely out of its home galaxy by a black hole's gravity, destined to spend the rest of its existence drifting through the emptiness between galaxies, entirely alone. Closer to home, there's a star that quietly reminds us just how personal these extreme events can eventually become. Betelgeuse, the bright, reddish star marking the shoulder of the constellation Orion, is a red supergiant nearing the end of its life, and astronomers widely expect it to explode as a supernova at some point, though the precise timing remains genuinely uncertain, anywhere from the next few thousand years to considerably sooner in astronomical terms. In late 2019 and early 2020, Betelgeuse dimmed noticeably, dropping to roughly a third of its normal brightness, briefly sparking excited speculation that the long-awaited explosion might finally be imminent. Careful follow-up observations eventually offered a calmer explanation. A large cloud of dust, ejected from the star's own turbulent, unstable outer layers, had likely drifted between Betelgeuse and Earth, temporarily blocking some of its light, alongside a natural dip in the star's ordinary pulsation cycle. When Betelgeuse does eventually explode, it sits comfortably far enough away, roughly 600 light-years, that it poses no meaningful danger to Earth at all. Instead, it would put on a spectacular, harmless display, potentially bright enough to be visible even during full daylight for weeks. A modern echo of exactly the kind of ancient guest star that Chinese astronomers so carefully recorded back in the year 1054. It's worth sitting for a moment with the question of whether events this violent can actually reach out and touch a planet like ours, and the evidence suggests, at least occasionally, they already have. Scientists have discovered unusual deposits of a radioactive isotope called iron, 60 embedded in ancient seafloor sediment and other geological samples here on Earth, an isotope that's extraordinarily difficult to produce through any ordinary, natural process on our own planet. The most convincing explanation is that debris from a nearby supernova, one that exploded relatively close to our solar system, millions of years ago, drifted across interstellar space and gently settled onto Earth's surface, becoming quietly incorporated into our planet's geological record. These particular explosions weren't nearly close enough to sterilize the planet or end life outright, but researchers continue investigating whether they may have subtly affected Earth's atmosphere or climate at the time, since a nearby burst of high-energy radiation can, in principle, alter atmospheric chemistry and increase radiation exposure at the surface. No dramatic mass extinction has been conclusively linked to these specific ancient events, but what makes the evidence so extraordinary is what it represents. Material forged inside the heart of a dying, distant star crossed the emptiness of interstellar space and became part of the actual, physical rock beneath our feet. Our planet, in a very real sense, has been quietly collecting fragments of cosmic catastrophes for its entire geological history, layered invisibly into stone that most people will never think twice about. There's something almost beautifully mechanical, worth appreciating for a moment, in how humanity actually manages to catch these impossibly subtle ripples in space-time at all. The detectors responsible for the very first gravitational wave detection use an extraordinarily simple principle, dressed up in extraordinarily precise engineering. A laser beam is split into two paths, sent down a pair of perpendicular tunnels, each several kilometers long, then reflected back and recombined. Under ordinary, undisturbed conditions, the two beams cancel out almost perfectly when they meet again. But if a gravitational wave passes through the detector, it stretches one arm by an infinitesimal amount while compressing the other, throwing the two beams very slightly out of alignment, a mismatch smaller than 1/10,000th the width of a single proton, and yet, remarkably, still detectable, thanks to decades of extraordinarily careful engineering designed to filter out every conceivable source of ordinary, earthly vibration, distant traffic, seismic tremors, even the gentle crash of ocean waves against a coastline hundreds of kilometers away. It's a strange kind of instrument, built entirely to measure something that, for the vast majority of human history, nobody even knew was there to measure at all, listening patiently for a disturbance in the shape of space itself, small enough to have gone completely unnoticed for the entire span of recorded human history, until the technology finally caught up with Einstein's century-old prediction. There's one more thread worth pulling before we let all of this rest, because it ties almost everything we've explored tonight together into a single, quiet idea. The most destructive events in the entire universe, the ones capable of erasing a star completely, of tearing another star apart thread by thread, of shaking the fabric of space-time itself, keep turning out, again and again, to also be engines of creation. Stellar explosions scatter freshly forged elements across space, elements that later planetary systems depend on entirely. Colliding galaxies compress gas into vast new populations of infant stars. Neutron star mergers manufacture some of the heaviest, most precious elements in the periodic table, material that eventually finds its way into rings, into circuitry, into the geological record of entire planets. Even the violent activity surrounding an active black hole can redistribute matter across an entire galaxy, quietly shaping where its next generation of stars will eventually form. None of this makes the destruction itself any less real. Stars really are erased. Galaxies really are distorted almost beyond recognition. Matter really is thrown across distances too vast to comfortably picture. And yet, the ongoing evolution of the universe seems to depend entirely on this continual, violent recycling. A universe where matter remained permanently locked inside its very first generation of stars would look nothing like the one we actually live in. Much of the complexity around us, every heavy element, every rocky planet, every ring on every hand, exists specifically because earlier cosmic structures were violently broken apart, and their material was gathered up and reused. Catastrophe and creation, out here, were never really opposites. They're simply two consecutive stages of the very same, patient, ongoing process, playing out across timescales too enormous for any single human life to witness beginning and end. And with that, we come to the end of tonight's journey through some of the most extreme events the universe has ever produced. We've followed stars all the way to the final moments of their lives and watched entire galaxies gradually reshape each other under nothing but the patient pull of gravity. We've sat with matter pushed into states so extreme that no laboratory on Earth could ever recreate them, and let signals that have been traveling for millions, sometimes billions, of years finally arrive here, tonight, to be quietly considered before you drift off. Some of what we explored tonight lasted only a fraction of a second. A chirp of gravitational waves, a burst of gamma rays gone before a telescope could even turn to look. Other events unfolded over timescales so vast that no human lifetime, no human civilization, could ever witness their true beginning and their true end. And yet, from here, from this quiet room, we can still detect nearly all of it. Ancient light finally reaches us across the dark. Radio signals arrive patiently at waiting telescopes. Gravitational waves move silently through the very ground beneath you, right now. Tonight, disturbances from collisions that finished before our solar system even existed. For now, though, none of that needs your attention. You can let it all stay exactly where it belongs, out there, distant, unhurried. Let those galaxies continue their slow, gravitational dance without you. Let the stars keep following paths they've been traveling for millions of years, paths that will continue on, quietly, whether you're awake to think about them or not. Nothing out there requires anything from you tonight. Let your breathing settle into something slow and easy. Let your shoulders soften a little further into whatever is holding you up right now. Feel the surface beneath you fully supporting your weight, exactly as it is, and let the last remaining thoughts of the day become smaller, quieter, and steadily less important. Here is the mirror I want to leave you with tonight. Every element inside your own body, every trace of iron in your blood, every fleck of heavier metal woven quietly into the world around you, was forged somewhere out there, in exactly the kind of violence we spent tonight exploring. Some of it came from a star's calm, patient burning over billions of years. Some of it came from something far more sudden, a core collapsing in under a second, two dead stars colliding after a billion years of drifting slowly toward each other in the dark. You are not separate from any of this. You are, quite literally, made from the debris of events like the ones we spent tonight walking through together, catastrophes so old, so distant, that their light finished traveling long before there was anyone here to see it arrive. And now, that same ancient material is doing something the universe seems to do everywhere, endlessly, patiently, resting, reorganizing, and eventually, quietly, beginning again. If you enjoyed this journey through some of the universe's most extreme events, you're always welcome to like this video, subscribe to Somniora Mind, or leave a thought in the comments below. It helps more curious, sleepy minds find their way here too, one quiet mind at a time. Rest now. You've earned it. Good night.